All right, yeah. So thanks for having me, and I'll be talking about this joint work with Arthur and Mark from UCL. And yeah, I guess I'll just like get into it. So I guess kind of the headline result is this uh, gamma to zero kind of claim that we have. Um, so this is from this paper by Bravi and Ha like a long time ago, where they kind of show how if you have some code that has transversal non-Clifford gates, then you can use this to define a magic state distillation procedure where the cost of the procedure is this thing that has the exponent, which is like just depending on the parameters of the code that you're using.
Mm-hmm.
And so this is kind of telling you that if you have a linear rate and you have your distance growing as your code size grows, then this can allow you to define some procedure with constant overhead. And this is kind of what we make a code with these kind of parameter scalings and the transversal non-Clifford gates, or at least like a family of codes. But we're okay, we're not the only ones. So kind of concurrently, there was like three other results that did the same thing. Actually, we were the last ones. So this was the first one, and then this is kind of the most complete one, I guess. And then the other three are all kind of rushed out to be concurrent with this first one. So it has the most details in it. But I have like a bit of a summary of the kind of differences or similarities between these. And I guess the main thing that I want to point out is that our construction is very different to the other three. So they're all algebraic constructions. They work by these kind of like puncturing over higher fields and things like this. They don't give you LDPC codes, and they give you you have to do like a physical CCZ gate to do your transversal non-Clifford, but they will give you linear distance as well as linear rate.
But two dimension 2 to the power of 10 seems pretty stiff, no?
Right. So they you can they show how to implement this by just using 10 qubits to simulate the 2 to the 10 dimensional qubit. So it's yeah, you don't need like a physical 2 to the 10 dimensional qubit. Yeah. And yeah, so the kind of the good things in our construction is that they are LDPC, and you only need these like non-entangling single qubit operations to do the gate. But the distance scaling is really bad. And I guess I should also say these are, the LDPC in like the technical sense, but like if you ask an experimentalist to build this thing, they're not going to be very happy with the weights. So it's not like practically LDPC, but it is like technically LDPC.
Can you give us some numbers?
Can I give you some numbers? I can give you maybe I like not an exact number, but I think probably you'll have checks that are like on the order of hundreds of qubits.
Gotcha.
Yeah, I mean, even just in like high dimensional color codes, you have like 40, 50 body checks. So
yeah. And this is all the kind of all the steps on the gamma going to zero setting. Whereas there was this previous work by what is it, Hastings and Ha that had a pretty small value of gamma, but not zero.
Yeah, they
0.6 something. But I mean, in the end, I mean,
yes.
that's what this means is like what the actual overhead is that you would get in a practical, realistic protocol, right? So at the end of the day, I guess the actual numbers matter, right? Can you comment on this?
Yeah. And also, yeah. So like obviously, yes, you're gonna have some coefficients on all of these things which are going to be relevant. And this is like a going to zero in the limit that your code is infinitely big, which practically you're not going to have. This one, at least this first one, they show that actually you can get equal zero finite sizes. And this is because they give some arguments about not needing to do these like concatenation steps, and you can basically just do like one round. And the output you get from this one round is good enough that you don't need to concatenate. I should say as well, like I don't really understand like all these other constructions. particularly well, so I can't really answer too many questions about these.
Mhm.
This slide. I think basically everything that's in this table is like pretty much the extent of my understanding of these constructions.
But what about the dimension scaling? Maybe I've missed that.
The dimension scaling in what sense?
The dimension
like
of this
here?
class of codes, all of those.
The
You only
dimension
have
like
the code,
of the qubits.
the logical dimension.
Oh, right. They're all linear.
Okay, thanks.
Yeah. So because this is necessary for gamma to 0, you need like a linear rate. Yeah. Yeah. Okay. So anyway, that's kind of the high level summary. The other caveat that I need to mention is the what you will get when you do this gate is like a non-Clifford operation acting on a linear number of logical qubits. But practically what you get, in our case at least, is this like operation that's performed is some big mess of like many, many overlapping CCZ gates. And like practically how you should use such a state in a magic state distillation procedure, or like how well it can be turned into some like disjoint set of CCZ states or something like this is not really obvious, at least at the moment. So whether like you can it actually is going to 0, or whether it's, it has the necessary conditions, but it's not sufficient, you need a bit more, I think is not really clear just yet. So this is something that to keep in mind, it's something that was pointed out to us after we put the paper out. Okay, so I'll start with kind of this question of what are rainbow codes, and the answer is that they're generalized color codes, but this doesn't really answer very much because there are many generalized color codes, and that this is not really all of them. This is just some selection that I kind of arbitrarily picked, and obviously people in this group have worked on generalized color codes as well, so sorry if I've missed any of your results in here. But this is some kind of like rough sketch of all the things that there are.
Is a Floquet code a different code? That's an interesting perspective. Yeah, maybe.
I kind of think of Floquet codes as, in some sense, coming from the color code. I mean, certainly like the original Hart-Hastings one is using this like 3-colored hexagonal lattice to do all the scheduling and stuff, right? And then like people in this group have work of like directly making Floquet color codes and all this kind of thing. But I certainly think of them as like very connected to the color code. But yeah, anyway, so what we're going to be doing is adding a little bit here coming from the pin codes, and we'll also do some of this and combine with these quasi-hyperbolic things from Guanyu Zhu and some other people from IBM. But so maybe then a better question is what are color codes? And you can give many answers about how they're cellulations of manifolds, or their chain complexes, or their topological phases, or whatever. But I don't really want to think of any of this. I just want to think of it as a colored graph, and also 2 numbers. So what does this mean? Well, here's some kind of standard color code lattices that you're probably familiar with. And I want to reinterpret these as, instead, these are just 3-colored graphs, and you're going to put qubits on the graph vertices. And then instead of kind of assigning some geometry to this and talking about faces or any like kind of dimensional object, you just say the stabilizers are going to go on the 2-colored subgraphs, right? So we want to abstract away from all of this sort of geometrical perspective, and we want to just only think about colors. So here's some higher dimensional examples. So you can think of the 832 code as being, you put an X stabilizer on the unique 3-colored subgraph, which is just the whole graph. And then it Z stabilizers on all of the 2-colored subgraphs. You can kind of do the same going to the 4-dimensional version of this hypercubic color code. And you can kind of see here the connection between like number of colors and sort of dimension of cell in the traditional picture of how you think about color codes.
So maybe this question. Just
sure.
To not get lost, what exactly are you coloring? So you said the vertices, so a graph has vertices, edges. Usually
Sure.
people
Yeah.
convert
So
coloring, but now it seems to be a different notion of
right.
color.
So yeah, this is we're talking about an edge coloring, right? So in all of these cases, you're coloring edges so that every vertex it never has like more than one color of edge connected to it, right? And actually, in these cases, every vertex has exactly one of each color of edge. If you were to introduce some kind of boundaries, like if I was going to cut this lattice here, then now these ones they'd be missing like one color, right? I'm not going to think about boundaries at all in this talk, but I think if you do want to think about boundaries, this is how you should do it, is you start removing certain colors from certain vertices. Yeah. And I should say as well, what we're going to, like, this is colorable in this sense, right? Where each thing is exactly one color of edge. We're not going to need in general the graphs to be like colorable in this sense. And in fact, the cases where they're not are really the cases that we're interested in. So you'll see what I mean by that when we keep going. Anyway, maybe this is some kind of general description for some kind of color code object that forgets about all this geometry, right? You take a graph that has some d+1 colors of edge on this graph. You put a qubit on every vertex, and then on like my d-colored subgraphs, I put every d-colored subgraph is an x stabilizer, and every 2-colored subgraph is a z stabilizer, right? This is like some first attempt to do this. And this is actually just another way to describe a pin code. So pin codes already exist, and they're kind of more traditionally defined in this way. So you instead think about, I have some simplicial complex where I have d+1 colored the 0 simplices. So every d simplex is going to have d+1 0 simplices, the part of it, and then each of these should have a unique color. So there's no 2 0 simplices with the same color that are part of the same D simplex. And then given this like colorable simplicial complex, you're going to pick 2 numbers, x and z here, that are going to satisfy these requirements. And then you assign your x and z stabilizers to what they call x or d minus x and d minus z pin sets. And a pin set is just, I pick some like I simplex, and then it's the set of all the D simplices that contain this I simplex. And then you call this an I pin set. So I can give you some example here. Oh, okay, I've done this in a weird order, but I'll just skip to here. So this is an example of a 3-colorable simplicial complex. So this is a 2-dimensional simplicial complex with 3 colors. And like this, every 2 simplex, every triangle has 3 different colors of vertex. And for an example, a 0 pin set would be like this vertex. It would be these 8 2 simplices that are associated to this vertex. That would be a 0 pin set. And then this pair of 2 simplices that are associated to this edge would be a 1 pin set. Was there a question?
Can you comment on that, how this relates to like a acceleration of a manifold? Because you need to have this to make a consistent coloring somehow, no?
No, not necessarily. So yeah, you'll see this in a little bit. That's going to come up.
Okay.
Okay. Yeah. Okay. So that's just the idea of the pin sets. Is you pick some lower dimensional simplex, and then all of the like highest dimensional simplices that contain this are going to be part of your pin set, and these will be where you're going to put your stabilizers. So what I want to do is kind of turn this into a dual picture, where instead of, we want to take this complex and turn it into the kind of graph that we were looking at before. So the way we're going to do this is we're going to change every D simplex into a vertex. And then whenever 2 D simplices meet at a D-1 simplex, you join them with an edge between the 2 corresponding vertices in this dual picture. And then we color each edge depending on which color of 0 simplex is not contained in this intersection. So again, here's an example like this. So every 2 simplex has now become a vertex. And then if they share a 1 simplex, then you join the vertices with an edge. And then this 1 simplex contains like a red zero simplex and a dark blue zero simplex, which means you color the edge light blue and then the same. This one would be red because it's not the colors in this edge, and like this one will be dark blue because it's not the colors in this edge, right? So this object we're going to call the simplex graph, and this is kind of encoding all of the information about the structure and the colorability of this simplicial complex, but just in a kind of a dual picture. So then maybe here is more like what Jens was asking about. This would be an example that's not a cellulation of a manifold. So all I've done to make this is I've taken every red vertex and I've doubled it. So like, for example, this red vertex, I just make a copy, and the copy is connected to the same vertices as this one. So it's just kind of, these ones are not doubled, but all the red ones are doubled. So this thing is not a manifold because it's kind of two sheets that are just glued together at some points, but not at other points. And if I was to take the simplex graph of this guy, it would look like this. So what's happened here is now sort of before we had just this, this became one vertex, this became one vertex, they're joined by one edge. Instead, there's 4 two simplices here in this region. So each of these becomes a vertex, and then they all meet at this common one simplex. So that means the vertices in the graph are going to form like a size 4 clique, and all the edges in this clique are going to be the same color because this edge has the same 2 colors of zero simplex in it, regardless of like which two simplex. Sorry, which two simplex we look at. So you can kind of take away that, and this looks a bit clearer. So this is what we end up here. And what you want to notice, I think, and again, this kind of goes back to Jens's question, is this thing, which is not a manifold, this is still a valid colorable two-dimensional simplicial complex, right? Every two simplex in here still has exactly 3 colors of vertex, and they're all unique, right? So you don't need this simplicial complex to be a cellulation of a manifold in order for it to be 3 colorable in this way. But the graph that comes out of this is no longer like a 3 colorable on the edges graph, right? Because now like this vertex contains multiple red, or is part of multiple red edges, right? And actually all the vertices are part of multiple red edges. So this is kind of the thing to be aware of, is the simplicial complex is always going to be 3 colorable, even when it's not, like D colorable, D+1 colorable, even when it's not a manifold. But the graph that we get out, this doesn't have to be true. And then this is going to kind of lead to some extra insights that you get maybe from the graph that you don't get from the complex. And you'll see what these are in like a little bit. So actually, you'll see what they are maybe right now. So we have 2 kinds of subgraph that we're going to be particularly interested in. So the first one is what I'm going to call a maximal subgraph. And this is kind of what we looked at before. This is like what we were implicitly talking about, which is I pick some subset of colors, and then I find some maximal subgraph of the whole graph that contains only those colors. So this would be a maximal light blue red subgraph, and this would be a maximal dark blue red subgraph. Then there's a second kind of subgraph that we're going to care about, which is what we call a rainbow subgraph. And this is when every vertex in the subgraph contains or is part of exactly one edge of each color in this set. So this would be a light blue red rainbow subgraph. This would be a dark blue red rainbow subgraph. And then this one in the middle is kind of a special case, because this is both a rainbow subgraph and a maximal subgraph. And this is because if we go back to here, you can kind of see each of these vertices that's part of this subgraph is part of only one dark blue and one light blue edge. So this thing is both a maximal subgraph and a rainbow subgraph.
Sorry,
But the other two-
sorry, that's a stupid question, but I missed
Okay.
like In what sense it's a maximal subgraph?
Okay,
Uh,
it's maximal
no,
because
okay, that's consistent. Okay, that's two colors of an edge.
Yeah.
Yeah, oh, right. And then you have like each color in the okay,
like
fine.
yeah,
Okay.
like there's no more red or light blue edges
Good.
connected to any of these vertices that I can add to the subgraph.
Good. Sorry, I was slow. I get it.
Okay. And something important that we want to notice is that this idea of a maximal subgraph is the same thing as a pin set. So you can kind of see, I'll recall the definition of a pin set here, and then we can compare this graph to the complex that it came from. And you can see, for example, if I take this like 0 pin set associated to this dark blue vertex, it's the set of all of these two simplices around it that contain it. And that's the same thing as this maximal light blue red subgraph. And you can sort of see that they're the same because if I say like, you know, what is this? It's the set of all the two simplices that contain this vertex. And what is this? Well, I can start at like one of these vertices, which corresponds to a two simplex containing this vertex. And then I'm allowed to explore in this graph to all the other vertices I can, as long as I don't ever move along a dark blue edge. And moving along a dark blue edge is the same thing as moving to a two simplex that contains a different dark blue vertex and doesn't contain this one. So this idea of a maximal subgraph is exactly the same thing as this idea of a pin set. So if you're going to define a pin code on a graph like this, you can just take all the maximal subgraphs of like whatever size subset of colors you like, and you associate stabilizers to those maximal subgraphs. So here's a kind of a more general statement. Sorry, was there a question?
Yeah, since you hinted at it and in your previous sentence, my question is like, how important are different values of S? I'm not too familiar with the pin code construction. So
Okay.
you can just pick any S you like, and then you put stabilizers on it. I guess there is some, like if it's D or if it's like code D0, like D minus. Yeah, if it's 0.
Yeah, so that's kind of,
like,
no, exactly. So that's kind of what I want to talk about here is the S is, you know, when I'm talking about S here, S is a set, right? But really, for most of the time, we just care about the size of the set. And then you associate kind of equivalent things to all different combinations, right? Certainly in the pin codes, this is true. So what they would do is they would say, like, I mean, go back to the definition, right? They would say every D minus X pin set will be an X stabilizer, and every D minus Z pin set would be a Z stabilizer. In the case of 2D, the only numbers you can pick for X and Z is 2 for both of them. So it's just every 0 pin set is both an X and a Z stabilizer. So in this case, it's the same as saying every face, if you like, in this graph is an X and a Z stabilizer, right? Because each of these two colored cycles is associated to one vertex in the complex. And then all of the two simplices that contain this 0 simplex are the 0 pin set for this 0 simplex. So that's what you put your stabilizers on, right? Does it make sense? Yeah, so they don't care about the colors at all. It's just like equal to all of them. But again, this ability to care about the colors is what's going to make what we do more general than the pin code construction.
But until now, you're basically finding a new language for pin codes, right?
Yes. Yeah. Yeah. So yes, right. So yeah, what you can do is you can talk about you just take like the size of S, we'll call this K, and then a K maximal or K rainbow subgraph is any S maximal or S rainbow subgraph where K is the size of S, right? And then this is kind of the most important thing to remember going forwards, is that you can show that if you choose X and Z in the same way as with the pin codes, then the non-trivial vertex intersection for any X maximal and any Z rainbow subgraph, or the converse, must have even size. So, and I'm not going to give you like a super rigorous argument for why this is the case, but kind of the way to think about it is like, if I have some X maximal subgraph with some number of colors, because of this, if I take some other Z rainbow subgraph, X and Z, there's two sets of colors in the two subgraphs, must have at least one shared color, right? Because there's only D+1 colors in the graph, but this has to add to D+2 or more. So they must have at least one shared color. And this means if they have one vertex in their intersection, I can look at this vertex, because it's part of the Z rainbow subgraph, it must have at least one edge of this shared color coming from this vertex is part of the rainbow subgraph, and then all edges of that color coming from it are part of the maximal subgraph. So I just follow the unique edge that's part of both, and then I find another vertex at the other end, and now I have like a pair. And then in this way, I can partition the whole intersection into just pairs that are joined by this shared color. And then this is going to guarantee that the intersection size is even. And so what does this mean? It means that if we have a pin code, then all X and all Z rainbow subgraphs that are not also maximal subgraphs have to be the support of logical operators, because every X or Z maximal subgraph is a stabilizer, and every X or Z rainbow subgraph commutes with all of them because the intersection is always even by this. So, unless in the case where they're the same thing, the rainbow subgraphs have to be logical operators.
But
so
there's also like a further delayed answer to the question of Julio, right? On the catenary path.
Yeah. Yeah. So like this light blue, dark blue guy here is an example of a maximal subgraph that is also a rainbow subgraph, whereas these two would be examples of ones that are not. Oh, I actually had this here. Okay, so there you go. You can see this. So these would be logical operators in such a code, whereas this would be a stabilizer. And the case where all rainbow subgraphs are also maximal subgraphs is exactly the same as the case where your simplicial complex is a cellulation of a manifold. So this is kind of coming back to what Jens was asking before. And this is just exactly the case where you have a color code, right? So if I have a pin code that is not a color code, then it must have logical operators supported on these rainbow subgraphs. And this has some consequences. And in particular, this is kind of taken from the original pin codes paper. And it's a bit hard to pass. But the main thing to see is like, so these like different, the capital D is like code dimensions. So they're using the hypergraph product to define like different dimensions of pin code. And then the small d is the distance. And if you look at, for example, the plus, you basically see that it's all just distance 4, except for some special cases down here. And in the special case, the rate is constant, or the rate is 0, right? Like it's linear, sorry, it's constant k. So the rate is like asymptotically 0. And these cases are exactly the cases where you have color codes. And then the other cases where you're getting some kind of linear rate, you just have a constant distance. And this is because the rainbow subgraphs are like local features of the whole big graph. And when you grow your code, you're not growing the distance because you still have these local logical operators living on the rainbow subgraphs. So there's a pretty, oh yeah, sorry.
Yeah, so how many of these are there typically? I mean, I don't know what construction they use there. Maybe you're gonna to comment on this, but also in like balanced product code constructions, you have to like you have to promote some logical operators to stabilizers to get a proper distance scaling. So that's
Yeah, so I think it's probably similar. The way they're doing it here is they just take the hypergraph product and then they like subdivide it. We're going to do the same thing in a bit, so you'll see more on this. But yeah, essentially you have, if you construct them in this way, you have linearly many of them. Because they're just like local features of the graph. So and it's some, like periodic or something, right? So as you scale it, like you'll just keep getting more and more. So this is why the rate looks linear here. But the distance is constant because you're just adding like more and more and more of these little local features that are distinct logical qubits, but are just like locally living in the code. Okay, so we're now ready to talk about what are rainbow codes. And it's basically just you take one of these graphs that we've been looking at, you take these two x and z integers, and then you're going to assign your stabilizers to the maximal subgraphs, but you can also put them on the rainbow subgraphs. So here are just some kind of classes of example. If you take just the x maximal and x and z maximal subgraphs to be where you put your stabilizers, then you just recover pin codes. Then we have two classes we call generic and anti-generic, and this is where you put your x stabilizers on all of the x maximal subgraphs and your z stabilizers on all the z rainbow subgraphs. So this is like you take all the logicals that were living on the z rainbow subgraphs and you promote these to logical operators. This is the case where you do the opposite. So you just take all the ones on the x rainbow subgraphs and make these logical operators. And then this is kind of the most vague category, but this is where you find some other set of, like you pick some commuting set of x rainbow and z rainbow subgraphs, and you make these logical operators. So there'll be kind of some on both. And then in this case, it's really going to depend on the specific colorings. So we'll see some examples of this later.
Can I be really annoying
yeah.
and ask that intuition you were talking about on the last slide as to why pin codes have this constant distance? Can you just say that again real quick?
Okay, so it's just because every z and x rainbow subgraph is the support of a logical operator.
Yeah.
And the construction that they're using to generate simplicial complexes to define their pin codes on means that you have rainbow subgraphs of constant size in the size of the simplicial complex. So this is not like a general feature of all pin codes. Like an obvious counterexample is that color codes are pin codes and color codes don't have constant distance. But you could, in principle, you could define some graph where it has rainbow subgraphs that are not maximal subgraphs, but the size of these rainbow subgraphs is growing in the size of the code. But this is just not what you obtain from like using the hypergraph product to define your code. Maybe there's some other way to do it that would give you growing distance.
But by construction, each of these four cases contain the color codes, right?
Right. Yes. Exactly. So,
Mm-hmm.
Yes. This is kind of the main thing to see here is each of these four, in the case that rainbow subgraphs and maximal subgraphs are the same thing, each of these four reduces to just the normal color code. So, when you say like pin codes are generalizations of color codes, this is true. But now you can see that this is like one axis to generalize the color codes along, but there's many others that you can also pick. And this, we'll see that some of them are maybe a bit more useful. So yeah, the next thing I wanted to talk about is what is the hypergraph product. So this is where we're going to get into some more kind of clear examples of what we're doing and how we make explicit versions of these codes. So maybe you're familiar with it kind of using these kinds of things as some like tensor product of chain complexes. Again, I don't want to think about it this way. I just want to think about a product of graphs. And it's specifically a product of bipartite graphs. And I'm going to use this vertex labeling in this way. So you can think of these as classical codes where like, one type of vertex is bits and one type is checks, or you can just think of it as a bipartite graph.
And what was the meta message of your chain complexes that you flashed and then?
Well, this is just to say, you know, I think many people think about the hypergraph product in this way.
Ah, okay. And you're just not thinking this way. Good.
This is not how I want to think about it. Yeah.
Good. Perfect.
Okay. So when I take the product, I'm going to kind of carry on this labeling of the vertices just so that every vertex in the product has, I'm going to call this a level. It has a level that's equal to the sum of the levels of the input vertices that produce it, right? So this one is 0 plus 0, this is 0 plus 1, this is 1 plus 0, and this is 1 plus 1. And then if you take a product of 3 graphs, then you get vertices up to level 3, and so on. And you can think of this just as like an alternate way to view this chain complex kind of picture, where now these levels of vertices correspond to the dimensions of cells in your chain complex. And then you can derive a simplicial complex from this by associating one simplex, like one D simplex, to every path, starting at a level 0 vertex and then going increasing order through vertices up to level D vertex. So this path, just 0, 1, 2, would be 1, 2 simplex. Then there's another 2 simplex that's like this path. If you go to 3 dimensions, then there's like 0, 1, 2, 3, and all the other ways to go 0, 1, 2, 3, and those are all unique 3 simplices. And this is kind of equivalent to just subdividing your chain complex into like a D-dimensional simplicial complex, if you prefer to think of it this way. Maybe you also have seen this thing called the flag in other sources, or this kind of thing. But this is kind of the way that I want to be thinking about it. It's just this like sequence of vertices in the graph.
Just I mean, I completely understand. But I mean, this is anyway a cute picture of hypergraph products, right? I mean, even independent of your specific context, right? Good.
Yeah. Okay. And then right. So this is kind of the sequence that we're going to go through. So you start with your D bipartite graphs. You take the product to get a D plus 1 level product graph. Then you subdivide the product graph to get this D-dimensional simplicial complex. You take the dual of that thing to get this simplex graph that we looked at before. And then finally, you assign the stabilizers to your maximal and rainbow subgraphs to get your rainbow code. So here's like just an example to make the color code. You would just have D just cycle graphs. You take the product of all the cycle graphs, you get a D-dimensional hypercubic lattice. You subdivide that, you get just some cellulation of the D-dimensional torus by D simplices. Then the dual will give you some D-dimensional color code lattice, and then the stabilizers just go where you usually put them on the color code. But there's a bit more to be seen here, which is going to be useful. So what we want to think about instead is if I have, instead of just like D cycle graphs, I have D collections of disjoint cycle graphs. So like graph 1 is just a bunch of cycle graphs that are all disjoint. Graph 2 is a bunch of disjoint cycle graphs, and so on. And then when I take the product of all of these, every like D upple of cycles, like one cycle from each of the graphs, is going to give me one D-dimensional hypercube lattice. And I'll have like one of these for every possible combination of cycles that I can pick. And then you subdivide those, you'll get like D-dimensional simplicial cellulations, and then D-dimensional color code lattices, and then finally you'll just get many copies of the D-dimensional color code, right? And the nice thing to note is that up here, if my input graphs to my like rainbow code building construction all have even degree, then you can just turn those into this by doing a cycle decomposition, which is just you find some like basis, like cycle basis for the graph, and you split it up into those cycles. And then the question is just, if I can find some way to go back in this direction, because then I don't have to worry about doing all this stuff. I don't have to do all this stuff to get to my rainbow codes. I can just do whatever this thing is and go from having many copies of color codes to just kind of smushing them all together into a big rainbow code. And the answer to what is this thing is this is joining my color codes at domain walls. So what do I mean by this? I'll give you like a simple example.
Can I ask a dumb
Yeah.
question first?
Sure.
I'm just confused by some of the D's and D plus ones on the left. Like on the example
Okay.
where you had just the 0, 1 times 0, 1, and you said this gives us a square with 0, 1, 1, 2.
Yep.
This is a 2-level product graph, right? Or not?
Sure. Okay. I guess it has 3 levels of vertex, right? Because it has like 0, 1, and 2.
Okay. Cool.
Yeah.
That makes sense. Cool.
Yeah. Maybe
So-
this is like kind of, yeah, confusingly named, but yeah, I'm counting the number of different vertex levels.
Yeah, that makes sense.
I'm not saying that I understand this, but I find it plausible that these kind of constructions of rainbow codes based on hypergraph products give rise to these kind of color codes that are joined together at domain walls. But you're not saying that all color codes are informed. There's just a specific construction based on the hypergraph product, right?
They're
Or is
all
this-
rainbow codes. Yeah.
Yeah, sorry.
I'm saying that, yeah, given, like if I'm constructing them this way, where
Yes.
my inputs are all even degree graphs,
Yes.
and then I'm going to take the hypergraph product and do all this stuff,
Mhm.
then this is equivalent to just gluing together some color codes.
Mhm.
Yeah.
Okay.
But you could define rainbow codes that are not this.
Wonderful.
Sorry, I'm not used to talking so much. Okay. So here's the example that I'll give you. I just have 2 cycle graphs. And then I take the product, I get this square lattice. And then when I turn this into the simplex graph, I just get something that looks like this. So this is just the familiar like square octagon tiling for the plane, or for the torus, I suppose. And you can kind of see like this vertex is associated to like this 0, 1, 2, and so on. But if I was instead to take this product, so I have now 2 cycles here and 1 cycle here, then I get just like I get 2 square grids, like one in front of the other, and then the graph, the like simplex graph for this will look like just 2 of these color code lattices that are like placed one in front of the other, right? So at this point, I just have 2 disjoint 2-dimensional color codes. And then you're going to do something like this. So I'm just going to glue together in this graph these 2 vertices that are both just these 2 ones are going to get glued together like this. And this is going to transform this big product thing. So the square grids are going to get glued together down this line that I've colored gray. And the color codes get a bunch of new edges added. So you go from like these 2 squares being disjoint to having this kind of cliques joining these 4 vertices together. So this becomes some kind of weird cube. And the thing to notice is that everywhere except this line where I've joined them, this still just looks like 2 disjoint color codes, right? Only down this line is it different. And only down this line are the maximal subgraphs different from the rainbow subgraphs. Everywhere else is still, they're the same thing because it just looks locally like a color code.
But if you look at the
So-
2 graphs that you had before, how do you understand what's the
This
right
one.
gluing you can do? Like just by looking at these 2, you have 2 graphs that are the same,
Mhm.
and I guess different gluing, some of them will be better, some of them will not work.
So
How do
yes,
you-
yeah, we have in the paper, what do we mean by the gluing and what's allowed and what's not allowed is like very well defined. this is not some like operation I'm just making up and like looking at it and being like, oh, this looks like it's the right thing. It is all properly defined and explained and things like this. So basically you're defining the gluing on the input graphs. So the only rule for gluing the input graphs is that I can't glue together vertices that have different levels. So I have to glue like a 1 to a 1 or a 0 to a 0. And then what you can then show is that if you define some like kind of hyperplane gluing on the product, so this is like I take all of the vertices that are associated to this vertex and glue them to all the vertices that are associated to this vertex in this way, you can kind of show that this commutes with taking the product. So like gluing these two vertices in the input graph and then taking the hypergraph product is the same thing as taking the hypergraph product of these two and then gluing them to get this thing. Yeah. Maybe I'm already kind of running out of time, so I don't want to go like super into depth in this. But yeah, if you want to know like the full formal details of all the gluing and stuff, then it's all in the paper. And I think it's all pretty formal. So hopefully it'll satisfy you.
And the order doesn't matter, right? Of when you glue.
No, yeah, this is exactly the point, is that the gluing commutes with the product.
Okay, good. Yeah, my construction.
I have a maybe stupid question. Is that for the cycle decomposition comes with like some cycles and then some additional data describing how the cycles, like which subgraphs they were, how they were connected in the original graph. Are you using this information somehow for the gluing, like, or are you
so
not?
Yeah, what you do is you want to, right. What I'm kind of doing here is I start with these graphs. I do the decomposition so that I have all these disjoint cycles. And then I say like it commutes with the product. Actually, it commutes with all this stuff. So what I do at the end is just I do the inverse of whatever decomposition, like whatever, like this gluing I do down here has some like associated ungluing, which is the cycle decomposition. So I'm going to do like the way that I glue is the inverse of how I decomposed into cycles. And then the claim is that this commutes with like all this stuff I do in between. So what I end up with is the same thing I would have achieved if I had never unglued in the first place, right?
Okay, cool. So you actually use the input graphs, not only their cycles, kind of. Like, yeah.
Yes. Yeah. It's not just like you can give me, if you just give me like a bunch of cycles, you can glue them in many different ways, and these would all give you different codes at the end.
You know, if you could do even better, like instead of finding complicated input graphs for the product, I mean, complicated relative, but you know what I mean. Instead of this, just finding ways to glue, maybe even like an optimization problem kind of thinking, that you just take some cycles,
I don't know,
finding like the best way to glue them to give the best code, the best graph or anything.
No, I haven't really thought about this. Certainly, like everything we do is using these like input graphs as kind of a recipe for the gluing. But certainly, like, you don't need to do this. Like, you could define just some gluing however you like, that is not based on some input graph. And yeah, this is I think there's like many directions to generalize this stuff in beyond just what we did. Yeah. Okay. So I want to, so the thing I wanted to say is that basically the only place you have to make some non-trivial choice of where to put your stabilizers is down this line, right? Because everywhere else, a maximal and a rainbow subgraph are the same thing. But down this line, they're not the same thing. And so here you have some freedom of choice of like, I'll put some stuff on maximal things and some stuff on rainbow things. And how you make this choice is going to affect the codes that you get out. So I'm kind of abstracting away now, and I'm just thinking about like, this is a manifold and this is a manifold, and I'm gluing them together down this line. And then I'm going to choose this choice of where I put my X stabilizers and Z stabilizers. And you don't need to like fully understand all the details of this choice, but the thing to understand is what it does to the logical operators. So what you want to think about is there's like two kinds of logic. Well, there's like, many colors of, in this case, they're all strings, right? There's each like color of string going around some non-trivial cycle of the torus, or of the more general manifold, will be a logical operator. And there's sort of two ways that you can have these operators going. Either they're running parallel to the way that I've glued, or they're kind of running perpendicular to it, like this. And for the ones that are running parallel, the way that they transform is like this, given this assignment. So if the logical operator is on the left-hand side of this join, and it has a color that is C0 or CD, so these are just like, associated to the vertex levels, right? There's one color for each vertex level. If it has color that is C0 or CD, then you can't just freely move it over the join. Like, this thing on this side is an inequivalent logical operator to this thing on this side. But for any other color, they are equivalent. And then for the ones that are going perpendicular to the join, if the color is C0 or CD, then like this thing was originally a logical operator of like left torus before you glued it. But when you glue it, it will be detected by some stabilizer that lives here on the seam. And the same thing for this one. But the product of them now, these will cancel. So this will still be a logical operator of the whole thing, but these individual ones are not. So another way you can think of this is like, if I have some like anion and I move it along here, when it meets this join, it has to branch into three guys. It can't just like move freely through, right? Whereas for all the other colors, this is not the case. They can kind of move freely through it however they like. So this is the picture to keep in your head about what happens to these different logical operators with different colors when they interact with this join, right? And this is the sense that you can think of it as a domain wall. This is just some set of rules about how the charges are allowed to interact with this specific region of the code. Here's like a 3D example. So you can kind of infer the behavior of the membranes based on like knowing they have to anti-commute with the corresponding strings, right? So now this cubes on the left and right, I'm thinking of these as being like a 3 torus. So every like front and back, left, right, up, down are going to be associated. So this string is actually a cycle, right? Like it's connected to itself at the ends. So this red string here is kind of like, this one, that it's allowed to just live on one side and it doesn't have to branch. Whereas this blue one is like branching through to live in the other torus as well as connecting back to itself. And then the ones that are going parallel, the red one is allowed to pass freely through and the blue one is not. The blue one is like locked to live on the left-hand side. And then the membranes just have to anti-commute appropriately with the strings, right? So the red one lives just on the left, so the red membrane lives just on the left. The blue one, because it goes all the way through, you have to be allowed to take the membrane through so that it can anti-commute on either side and kind of correspondingly with the membranes going this way, right? So you can kind of think only about the strings and know how the membranes should go. Okay. And then the codes you're going to get from doing this are going to have properties that look like this. So the size of the code is going to depend on how big your input graphs are, how many there are, and what degree they have, the number of encoded qubits is going to depend on the number of independent cycles that you had, as well as on top the topology of the gluing. And kind of the way to see why this number of independent cycles matters is because I'm starting with, you know, a bunch of all these disjoint color codes, and I'm going to glue them together. And some of the logicals from these original codes will survive this gluing, and some of them will get associated. So my number of logical qubits will go down. And so the more like original color codes I started with, which is the same, because every original one comes from some like set of original cycles, the more of the original color codes I started with, the more like logical qubits I end up with, and also how I glue these. Because maybe I could glue them in a way that makes like some new handles or something like this, which would then increase the number of encoded qubits. So then the topology also matters. And then the distance is going to depend on the size of these cycles that I started with. And this is because there's going to be, there's a message in the chat. Is this recent? No.
Oh,
Okay.
it was just from.
I was just checking. It's not a question. Oh, hello. Why can't I go back? There we go. Okay. Yeah. So there'll be some logicals of the final code, like, you know, for example, like here, right? This was a logical of the original code, and then it's also going to be a logical of the final thing after I glue. And this means that, you know, whatever was the size of this, like whatever is the distance of the original color code before I glued it, that should be the distance of my total code when I'm done with the gluing, because this thing is still going to be a logical of the total code. It hasn't got any bigger. So this is why your size of the like cycle length in the input graphs is going to control your distance of the final code.
And what are the constraints to like capital D, that this dimension of the simplicial complex? Is there?
This is just how many different graphs I put into my product.
But this is in principle freely choosable, no?
Yes. Yeah, but the more you put in, the bigger n will be. So n is scaling.
Yeah, I mean that's a trade-off in overhead, of course.
And actually this scaling, so size of the input graphs, the scaling is not too bad. Number of input graphs and degree of input graphs, the scaling is like absolutely insane. It's something like factorial to the power of something. Like it's math. So you don't really
more than exponential.
It's it's much more. So
you
don't really want
that
to
means
be
like
making D very big.
I mean, in the catastrophic of all sense, it's just not local, right? It's like really completely all to all.
It's not all to all. It's just like I don't know. If you think just in the like the color code, right? Like in this case, if I take, you know, here I have checks of weight 8 coming from the fact it's like a product of 2 graphs, and the nodes are like degree 4 in here or 2 in here, right? If you were to take the product of 3 cycle graphs, you're already at checks of weight like 48. And then if you go to 4 cycle graphs, they're like hundreds.
So I mean, this is kind of the trade-off, right? I mean, anyway, it would be like too good to be true. I mean, like you have all the properties that you would want for a good code, that for you get all from the pin codes, and then you on top of things on the beautiful scalings, you have like transversal T and T dagger gates and so on. I mean, there must be some drawback to this somehow, and the drawback is that you get pretty stiff like weights of your measurements somehow, right?
So realistically, I think you want to be, I don't think you want to take this D above 3. And I think you want to keep this degree like absolutely as small as you possibly can. Because otherwise it really explodes.
But then, I mean, one can also, pin Julio, one can decompose these high weight measurements into many lower weight measurements, but then it would be just many, right? This will also explode.
The explosion. And then you're, you know, like one measurement error in like these many measurements is going to.
Of course, then of course, the circuit level noise eats you up then, presumably. Okay, good, but
Yeah.
that's the
Yeah.
trade-off, right? I mean, your code is like a wonder weapon in all respects except this, right?
Well, so we'll see like some examples.
Okay, good. Sorry, maybe
yeah.
I was anticipating this. Sorry.
Yeah. Okay. So here's like just an easy one, which is just the product of 3 copies of this like figure 8 graph. And every cube in here is like the product of 1 cycle from each graph, right? So like this cube down here is like this cycle times this cycle times this cycle. And this cube is like a 3D color code that's then joined to the other cubes depending on like the gluings of these graphs, right? So like it intersects this cube because this cycle intersects this cycle, and this cube because this cycle intersects this cycle, and so on. So you'd when you unglued like these guys into just like 6 cycles, then you would get 8 color codes from the product, and then you glue them all back, and you get this one big thing where everything's meeting at these domain walls. And the logical operators of this guy look like this. So there's 3 independent colors because there's 4 total colors, but the 4th color is just a product of the other 3. And I'm going to look at the red one is like C0, and then the green and blue will be C2 and 3. So the red one is going to kind of transform in this sort of special way, and the blue and green will transform as these other ways. So the blue ones, the membrane, are going to move like when they intersect the domain wall. So like if you think this membrane here was like just belonging to this bottom left color code, but then when it meets the domain walls here, it has to kind of go through and it has to become this big global thing that lives in the whole code. And then the green one kind of does the same. And then the red string kind of also does the same. So the red string has to, when it hits this, go through and live in the other side. And this is going to guarantee that the intersection of the blue membrane and the green membrane is a red string. And then if you look at like this other example, so now this red membrane, because the red string lives like, it has to go through to this side, but it can't move, for example, down into this bit here, or it can't move back into the bit at the back. It means that the red membrane is just going to be contained just within like this top front bit, but it could move through into this side because it has to be able to anti-commute with the red string on the other side. And you can kind of similarly know that the green string has to be like this, and then this is telling you that your red membrane and your blue membrane will meet at the green string. And you can kind of check this for combinations. And this is guaranteeing you that you have the right intersections to make your non-Clifford gate work. Because this is what you need for the non-Clifford gate, is that if I take any 2 X logicals, the intersection has to be a Z logical. And this is kind of what you're seeing here. So it's sort of trivially true within each code because the 3D color code already has this property. And then just this choice of how stuff transforms in the domain walls is making sure that this like extends into the global structure properly as well. So like kind of an asymptotic example that you can do is if you take one of these like Q-regular expander graphs, because these have a number of independent cycles that is linear in the size of the graph, and then they have a girth that is like log of the size of the graph. So if you take the product of 3 of these, you're going to get codes with these parameters. So your rate is like the 2/3 power, or your k rather, and your distance is scaling like log n. And this is actually extremely bad. So this like log distance scaling is so bad that even though you have some like non-constant k, you can just take copies of the 3D color code and you can beat this. So this is, and at this point we were like a bit sad about this construction because we were like, it seems like we put in all this work making this thing, and then it's actually really bad. But luckily, this is not the end of the story. So what you can do instead is you can take some like, you use, oh, yeah, I have this reference here. It's hiding under the Zoom window. You can take this construction of like quasi-hyperbolic 3D codes, which is proposed by Guanyu Zhu and some other people from IBM.
And then what you said before, I mean, that's true for any Q regular expander graph. It's just a property of, it's just a graph theoretical property. That you have so many cycles. That's so? So you look this up in a graph theoretical.
The having linear number of cycles is actually true for any Q regular graph. It doesn't even have to be an expander.
Okay.
What it being an expander gives you is this log n girth. Because if you just like come up with some like family of Q regular graphs yourself, probably will have constant girth. And this is kind of like it from a you know, like a code construction perspective, this log girth is extremely bad. But from like a graph theory perspective, this log girth is like extremely good. This is like basically the best you can do on any graph family that is not just like a cycle. Yeah, so the way that this quasi-hyperbolic construction works is you take some 2D hyperbolic manifold, and this has an area A, and it has so it's a closed manifold, which means it has a genus that's order A, and it has a systole, which is like order log A. And then if you define a 2D color code on this manifold, you'll get something like this. But this is not going to have a transversal non-Clifford gate because it's only 2D. So to get the transversal non-Clifford gate, what they do is they take the product of this thing with a circle, and then this is going to give you some like quasi-hyperbolic 3D manifold, which I depict like this. So I have my 2D hyperbolic manifold is like this gray circle, and then you're taking the product with just this cycle, and it's going to give you something that's, I mean, I've drawn it like a cylinder, but you kind of associate the top and the bottom. I guess this is sort of like the thing that the ADS-CFT people draw, where it's like Euclidean in the one direction and hyperbolic in the other directions.
Mm-hmm.
And this thing has a size that is just kind of trivially the size of the manifold times the size of the circle. And they choose the size of the circle to be log of the size of the manifold. It still encodes a number of qubits that is just linear in the size of the manifold. And this is because taking the product with the cycle is only adding a constant number of new encoded qubits. And then the distance is just like the same because, you know, all the ones that come from the manifold have the same distance, and the ones that come from the cycle have that same distance because we chose the cycle to have size log A, right? So this gets very, very close.
I'm gonna ask a shockingly stupid question. I mean, that's not the type. I mean, I was once attending a field theory course in the US. There were only 3 students, and in the middle of the course, some friend of mine who's actually now running the autonomous driving at Mercedes-Benz in Germany, he asked a question that was so stupid, that revealed so badly that he didn't get anything in the course, that the teacher looked at him like shocked for a minute, cried, and left, not to be seen again on that day. It's like so bad. All his work was for nothing. So I will ask you a question this time. I mean, it's you do this on in this kind of 2D hyperbolic manifold with areas, but it's still not a holographic code, right? The way it's set up, it's just
no.
The tessellation would be of a hyperbolic manifold, but it's still a color code on this negative curve guy.
So for the holographic codes, they like you define this tessellation or hyperbolic manifold, but then they use these like tensor network pushing rules to like push everything out to the boundary. So all the qubits just live on the boundary of the manifold, and everything is just living on the boundary, but it's kind of defined from the bulk. Whereas in this case, you tessellate the bulk, and And then you just put qubits on the vertices of this tessellation, and you define a color code as normal. And actually, in this case, there is no boundary, because for this like property of the genus being linear in the area to be true, the manifold needs to be closed.
Yeah. Good.
Yeah. Okay. So here's kind of what the logicals would look like on this manifold. I'm representing the ones that go around handles in the manifold as these kind of like curves on the top. And then the ones that come from the cycle are these like vertical ones. And the membranes that anti-commute with them are like here. So you, for the red and blue one, you just kind of extrude the 2D guys up into the third dimension. And then the ones that anti-commute with the strings that go around the cycle are just like the whole 2D membrane. So you have only 3 ones that come from the cycle, right? One for each color. And then you have like a linear number of ones that go around the handles in the manifold. Yeah, and so they get very close to this linear rate. It's just like this log factor. And the way to get rid of this is to, instead of taking the product with a cycle, which is only giving like a constant number of qubits, no matter how big you make the cycle, you take the product of something that has like will add many new cycles. And this is just the expander graph, right? So we're going to instead take the product of hyperbolic manifold that has area A with an expander graph that has size S. And because it has size S, it's going to have order S independent cycles. So we decompose the expander graph into these cycles, and then you take the product with the hyperbolic manifold, and then you'll get like many copies of this code that we had here, right? You're going to get order S copies of the code. And so in our final code, we know we're going to have N is order AS, right? Because it's just like the product of a thing with size A and the times S. And then when we do the ungluing, we're going to get order S copies. And then we know that this has order AS logical qubits, right? Because there's order A logical qubits in each copy, and we have order S copies. And in particular, there's going to be order S C0 colored logical qubits in each copy. So these are like the red ones that I've drawn here. There's like order S in each one. And then when we re-glue, we're going to save some physical qubits by doing the gluing. And then we'll have a linear rate as long as we don't lose some extensive number of the logical qubits. And we know that we won't, because we're always gluing kind of along this like parallel direction to the direction that these like C0 colored logicals from the hyperbolic manifold live. And we know from all the way back here that the C0 colored logicals that are like parallel to the direction of the gluing are not associated across the gluing, right? So that means all of the C0 logicals that we had here going in this hyperbolic direction are still all independent logicals over here. So we still have order AS of these. So this is guaranteeing that we have K is order AS, and then the distance is just the minimum of the systole of the manifold and the girth of the graph. And then we just choose A to be the same as S. And then this is going to give you codes with these parameters. So this kind of keeps this log distance, but you now have a linear rate rather than this like slightly less than linear rate. This is just a
short question on this losing logical qubit. So say you have 3 colors, there is a third of logical qubits that kind of is still separated between the layers. But for the other 2 colors, since you picked the C0 gluing, they get identified, right? So you use it,
so
you lose
all
a
of
constant
the
fraction, but you preserve a constant fraction as
exactly yes
Okay.
So all of the like blue and green ones that are going in the same direction as the red ones, you now like these are all now equivalent between the copies. But yeah, the red ones are not. And then for the ones that go, you can kind of see here, here's some examples of the logicals, right? So the red one that goes the other way has to like live in all the copies, but the blue and green ones that go this other way do not have to, right? So, and then for the membranes, it's like reversed. So you'll have like this big, tall blue membrane intersecting like this green membrane, add this string, which is a red logical. Or if I were to take like two big, tall of the blue and the green, the intersection is this big, long red one, and so on. So this is, again, you can see that the properties you need for the gate are preserved. So yeah, then we just have some open questions. How efficiently can we use these states? I mentioned this at the beginning, like just because you get out like a logical non-Clifford acting on a linear number of encoded qubits, it doesn't mean that you can turn this into like a linear number of like disjoint CCZ gates, for example, or CCZ states. So how efficiently can you do this is open. This is kind of mentioned by many people throughout the talk, but like this is not the only way to make these codes or these complexes, right? There's other avenues you could pursue. And then, yeah, how much can we increase this distance while keeping things LDPC? Can you get this like holy grail of asymptotically good LDPC codes with transversal non-Cliffords? I think, who knows? But yeah, that's it. So thanks for listening. Okay.
Wonderful. Great talk.
Questions?
Very quickly
I have
before the
one. I mean, I have
questions.
like high-level questions.
Sorry.
I mean, on the last bit.
Wait, first Tom wants to speak.
But yeah, sorry,
Oh.
very quickly before the questions. I'm going to go to the toilet,
Oh, very good.
but I'll come back.
Yeah.
You can think of questions while I'm talking.
I'm gonna get a coffee.
Okay.
Then also go to the toilet.
I've got to leave in 5 minutes or so.
Okay, good.
It's just the two of us, Julio.
Ah, hello, how are you?
Good. I saw you texted me, but I was off yesterday, so I'm gonna read your message now.
Yeah, just it was about the argument on the graph. It's a bit
Do you want to spoiler your message or
No,
no?
leave it
No
as
spoiler?
surprise. Yeah.
It was different from Arthur talk.
Yeah, very much so. And
Very much.
more positive.
Yeah, more positive than expected, given
Yeah,
previous opinion.
that's true.
Now we should see Mark talking about this, just
Yeah.
to see.
But also the last expander thing, like adding like 2D hyperbolic and this, not the circle, but there's new also. Wasn't they didn't have this in Benasque. Anyway.
How do you know they didn't have it in Benasco? Because they
Okay.
didn't say it.
No, because Tom had the idea after. At least he told me about it after. That like, this we could figure this out. Teague, what's the policy on also Amanda maybe, like what's the policy on the
Okay.
on the gauging and stuff? The 2/2.
Are you going to speak to Dom sometime soon?
This evening actually.
Okay. Well, if you prefer to have Dom talk about it, get him to talk about it if he's willing.
Yeah, so I have to say I kind of like the idea to maybe have also an intern journal club for like the 2 papers. But
Yeah.
anyway, now that Tom is back, we can maybe postpone the discussion to some other time.
Good.
We were saying this the taking the product with the expander graph worked out in the end. Very nice. Like that it's
Yes, yeah. I was talking to you about this in Barcelona, right?
Yeah, right.
Yeah. I worked this out.
So that was open, right? Okay, nice.
Yeah, the next day, like after I saw you, I went to the Picasso Museum, and then I was walking around the Picasso Museum, like thinking about this the whole time. And then halfway through, I started to think like this actually does work. And then I bought like a notebook from the gift shop, and I worked it all out
That's
in the notebook.
Nice, but that's often like that. No, I mean that's even true for me. That I mean I have ideas at the lake and so on. I mean usually there's hard work that leads nowhere, and then I go to a lake or so, and then you walk, and then you have a kind of like high level idea.
Yeah, but the hard work is
Well, but then I
I
guess the hard work is needed nevertheless. Otherwise, we just sit there in the car and
yeah.
sofa. Okay. Anyway, it's super cool. I mean, I'm super excited about this. I mean, it's like I mean on the first question, like what does it mean for magic state distillation? The answer is
Right.
I
don't know.
I mean, does it have an implication? I mean, I ended my talk with
Yeah,
definitely
so-
maybe in Okinawa, so that's definitely maybe in the sense that yes, you have this gamma going to zero, and of course that has an implication on magic state distillation. But in the end, it's unclear like how the trade-offs are, and it might be just better to make a conventional setting with low weight measurements,
Yeah.
and not live with this crazy construction. Even though it's just nice to see that just by seeing what you can trade against what, it's a kind of a nice like extreme point of the possible trade-offs. Is that a fair way of putting it? Or
Yeah, well, so I think a big open question is like how practically how small can you actually get, right? Because what you really want, like ideally, is for the logical action to be like CCZ on 3 qubits, and then a different CCZ on 3 disjoint qubits, and then a different CCZ on 3 disjoint qubits, and then you get out some like linear number of triples with CCZ on each triple, but they're all disjoint, right? Which is not what we get. We get like this big horrible mess of like loads of CCZs overlapping everywhere. And then how many magic states can you actually get out of this? I think is not known. I think you can do some like measurements, and you can do like Clifford corrections, and you can do a bunch of post-processing, and you can hopefully turn this into some like nice number of separate disjoint magic states. But like exactly how many you can do, is it still linear? Is there like some better version where you can make it linear? Like, I have no idea. So that I think is like a big open question still. Yeah, and then this point about like obviously this is all in the asymptotic limit, right? Practically, how big do you have to go to actually be beating the existing procedures in practice, and is it worth it to actually go that big again? I think I don't know. And then obviously there's like many other avenues you can go in to make codes like this. I think one of the main things I took away from this is like the product, like approaching this from a product construction perspective seems really bad. Like when you just take the product of 3 expander graphs, you get something that's horrible. Like it's much worse than just having like just some color codes. And the case where we get this nice construction is when you take the product of like an expander graph with a hyperbolic manifold, and the hyperbolic manifold is not itself a product of 2 1D things, right? This is some other thing that is not a product. And so maybe if you can remove the product entirely and just have some, I don't know, you can just define like some like 3-dimensional simplicial complex in some other way, and then just define your graph on this, and you never even have to introduce a product at all. Maybe this is even better. Maybe the product is like really bad and you shouldn't use it. So I don't know. I think there's like many directions that you can take this in, and whether any of them will lead to something that's practically useful, whether this is just like a theoretical exercise at the end of the day, I don't know.
So
Remind me exactly again, what property of the expander graph you wanted at the end when you were multiplying it with the hyperbolic?
Good
Right.
distance.
So you want, first of all, you want something that has a linear number of independent cycles.
Yeah.
And you also want it to have a distance that is growing in the size of the graph. And basically at least as far as I know, the best kinds of graphs that have such a property is the expander graph, like irregular expander graphs, which will have a linear number of cycles and like log cycle size.
So you could so rather than timing your hyperbolic surface by this type of expander graph, you are hoping maybe somehow you might be able to skip the product bit and import these properties directly into a manifold.
Well, I mean, so then it becomes less clear what properties you need, because all these requirements that we have are kind of coming from the fact we're using the product.
Right, okay.
Yeah.
Okay.
But there could be, I mean, this is just, I mean, well, not just, but this is the way you've pursued to come up with all these beautiful insights and examples. But in principle, that's just one avenue of generating these codes via this hypergraph product construction, right? I mean, you could have done something completely different. Is that so?
Yeah. So you can, I mean, all you need is a d-dimensional simplicial complex where you can color the vertices. Any kind of construction that gives you such a complex, you can then define one of these codes on it. And yeah, we did it just from like subdividing chain complexes that you get from the hypergraph product. But anything that gives you such a simplicial complex is valid. So there might be many other ways and much better ways.
I have two questions.
I got a bounce, but thank you very much, Tom.
All right, no problem. Thanks for inviting me.
DJ, can you grab my laptop at the end? Will do. Thank you. If you stay to the end.
Okay.
So, my first question on this, what was just talked about, is there some hope to like modify I mean, like I'm just thinking historically in the construction of other code constructions, modifying a product led to better construction. So I'm wondering if you could use some regular expander graphs that have some shared symmetry with the cellulation of the 2D simplex tessellating the hyper, or that you choose to tessellate your hyperbolic manifold with, and then modding out stuff to get maybe.
So something interesting that you find if you like, so all of these fancy products, the kind of the base case is using them to make a twisted torus, right? Like if you take just a lifted product or balanced product of some cycles, you get like a twisted torus. And this gives you some surface code with increased distance, because the logical has to do like some detour to compensate for the twist, right? But if you do this with color codes, what you find is that the saving you get, or the distance increase you get in the surface code, you can think of coming from the fact that the surface code logicals are kind of on this like taxi cab metric, right? Where they can only move, because it's like a square grid, they can only move like horizontally or vertically. And the twist is kind of, let's say, vertical. So if they're going around the handle horizontally, to compensate for the twist, they have to stop going horizontally and go vertically for a bit, and then they can start going horizontally again. And then this like fact that you can't do both at once is what gives you the distance increase. Whereas in a color code, this is not true. And the logicals can just go on diagonals and things like this. And actually, if you put a color code on a twisted torus, the distance doesn't go up, at least for examples that I've checked. So it doesn't seem like this actually, at least in this very basic example, saves you anything. Maybe this is just some like weird feature of this like really simple example. And if you look at more, like something that's less topological, you'll start to see savings. Or if you take some like more complicated quotients or however you do this. But it's certainly not immediately obvious to me that it will like benefit you by doing this for generalized color codes in the same way that it benefits you for generalized surface codes.
Cool, thank you. Makes a lot of sense. And my second question is on the usage from, at least and like actually decoding question. what you, at least in the pictures, and what we also find in color codes in higher dimensions than 2, is that there is a big asymmetry in the distance of X and Z stabilizers, because one is a membrane, one is a string, for example. And depending on which, for which part of your protocol you want to use the code for, you can actually single shot decode it, right? Like if you want to initialize like an eigenstate of a membrane, that's like single shot. And specifically in context with these byte being LDPC still having like still being quite large stabilizers, this might be interesting too. Like, is there some logicals that are single shot? Do you know anything about the single shot properties? Do the strings branch enough? Probably not.
Yeah. So you have some strings which are still just strings, right? This is what's giving you just the distance is the same as like the distance before you do the gluing. It's some of the logicals are going to be completely unaltered by the gluing. So these strings will still be strings, and you will have all the usual issues you have in decoding things that are strings. For the membranes and for the strings that branch, I think you probably can single shot decode these.
Yeah.
So yeah, it's going to depend on the logical and whether it is still a string or not.
Interesting.
I see. Yeah, but unfortunately, the non-Clifford gate is a diagonal gate, so probably not.
Yeah, so the
like
non-Clifford
it's
gate
exactly the
is
wrong
always
gate you
going
want
to
to-
involve is always going to involve logicals that are strings. Yeah.
I mean, could one blockify the code to lessen the burden of high weights?
Yeah, so I think you can do this. There is some in a kind of funny convergence. Nat Tandy Vasudhakar, I think in some maybe a student that he's working with or something. When I spoke to him at Banaska, he was like, because I'd spoken to him previously about this, like the rainbow code stuff. I spoke to him at Banaska and he was like, yeah, I was working on this Flaquet codes project with a student, and I think it might be connected to your stuff. And we looked at it, and what he has is basically exactly just some instance of like a rainbow code. He obtains it from taking some product and then concatenating with some smaller code or something like this. But you end up with something that can be exactly described using our formalism.
Okay.
And then he does some Flaqueification of this. But what he found when he did the Flaqueification is most of the logicals do not survive.
Oh,
So he had initially some like very large number of logicals, but then when you do the Flaquet step, you kind of keep some of them, but most of them you lose. So maybe
okay.
there's some better way to do this, or I don't know. I mean, like, I think probably there is some fairly straightforward way to extend our construction into some Flaquet thing, because it still has like this whole thing with all the colors, which is kind of the way that a lot of this Flaquet stuff proceeds. But how useful it is, I think, is kind of an open question.
But I think
Okay.
there could be more hope than for just some generic LDPC code, because if you were to look at the repetitive, like the circuit that does the repetitive readout, is actually, if you want to do this efficient Flaquet from like a circuit level perspective, you don't want to look at a single round. But you want to look at many rounds and then find kind of reassignments of how you traverse through this diagram that preserve some logicals, which for topological codes, you can go in any direction. So since yours are kind of closer to topological codes, so locally, in like a region that's smaller than the size of the inputs that you used, you will have this property that they're freely movable.
Right. So
But-
something to I guess be aware of is if my inputs are like some regular, like Q regular, right? If this is more than 2, then it means at every point a gluing has happened. So actually there is nowhere anymore where it looks locally like a 2D topological code.
I see. So that's why they are so good in parameters, I guess.
Yeah, so it's kind of interesting that like
So that's
the whole
like
argument.
a burden and a good thing at the same time.
Yeah. Well, it is. I do find it kind of interesting that the whole argument is like, oh, it only looks like a 2D code at this point. It's kind of inductive, right? It only looks like it's a 2D code like everywhere except at this point. So you argue just the properties at that point, but then you do that everywhere. And then you end up with something that looks like a 2D code nowhere, but the argument still works.
Yeah.